Slide 1. Chairperson, staffs, and all the supporting organizations, thank you very much for giving us this valuable opportunity today. My name is Hisashi Otsuji from Toyo University in Japan. Before my talk, I would like to show you a picture. Slide 2. This is the lid of a cup of water served on my way from Japan. It says, this water is naturally purified by Jeju volcanic scoria. I was surprised by the Korean people's high scientific literacy. Scoria is not known among people in my country. Congratulations on the success of earth science education in Korea. Now, let me start my talk today. Slide 3. I would like to talk about a learning approach to climate change education inspired by the color solid and the analysis and synthesis of Leonardo da Vinci. Slide 4. My talk today is divided into two parts. In the first part, I will propose a collective learning approach to climate change education inspired by two central ideas. In the second part, I will present 4 examples of specific learning activities for students. My aim today is not only to discuss climate change, but to rethink what and how students learn to understand complex realities. Slide 5. Part 1. Slide 6. When we think about climate change, many different concepts and words are intertwined. Therefore, it is sometimes useful to step back and consider the broader category of disasters as a whole. As is widely known, there are cases in which large-scale volcanic eruptions can lead to climate change at the global level. On the other hand, even relatively small-scale events can be complex. For example, a landslide triggered directly by an earthquake may actually occur under conditions where heavy rainfall has already made the slope unstable. In this sense, many disasters can be understood as compound events involving multiple interacting factors. Slide 7. The National Research Institute for Earth Science and Disaster Resilience in Japan classifies these types of disasters in the following way. Climate change seems to be related particularly to the labels in light blue. However, it also appears that there are other important concepts beyond those shown in this classification. Slide 8. We might also add examples such as sea level rise or bushfires. In this way, a wide variety of phenomena can be considered, forming a very colorful landscape of climate-related issues. This raises an important question: how can we identify meaningful perspectives for understanding such a complex whole? In such situations, it may be quite natural to recall an idea we encountered in art education during our school years. Slide 9. This is known as the color solid. It organizes the seemingly infinite and unstructured variety of colors by introducing 3 attributes and locating each color within a 3-dimensional space. Slide 10. The first attribute is hue. When viewed from above, colors are arranged along a 360-degree circle. The familiar 12-hue color will correspond to this idea. The second attribute is saturation, chroma. This is represented by the distance from the central axis. The farther a color is from the center, the more vivid it becomes. Even among the 3 primary colors, yellow, red, and blue, saturation differs, with red having the highest saturation. The third attribute is brightness, value. Colors positioned higher along the vertical axis are brighter and have higher brightness, while those located lower are darker and have lower brightness. In this way, the color solid organizes the overall system of color by using 3 axes and locating colors within a 3-dimensional space. Now, even when we are faced with a seemingly complex collection of integrated phenomena, assigning a few meaningful axes and re-examining the whole from that perspective may deepen our understanding. Could we do something similar for the many terms related to disasters and climate change? If we can identify appropriate axes and organize the whole accordingly, we may take an important step toward a more comprehensive understanding. Slide 11. This idea is also similar to what we do in statistics. In principal component analysis, we mathematically identify the direction with the greatest variance in order to describe a complex whole. By defining the first and second principal components, we establish axes that help us represent and interpret the overall structure of the system. Slide 12. Here, let me show you a simple example. I have created a preliminary concept map of terms and ideas related to climate change and associated disasters. What do you find? The arrows indicate cause and effect relationships. Natural phenomena, and those closely related to them, are shown in yellow, while human-induced factors are shown in green. Some terms refer to meteorological phenomena, whereas others represent the disasters that result from them. The impacts may be limited to a particular region or may occur at the global scale. So, students may notice that there are cause and effect relationships, labels can be classified, and the extent of damage caused by a disaster varies greatly. In this way, by identifying possible axes within a complex and integrated problem, organizing the elements, and then revisiting the whole, we can begin to find meaningful entry points for understanding the overall issue. Such diagrams will naturally differ depending on who creates them and on the members of the group. And that is perfectly acceptable. In today's talk, I argue that this kind of activity has significant educational value, and that it should be positioned at an early stage of learning as part of the analysis phase in students' inquiry. Slide 13. When thinking of someone who used analysis as a method, Leonardo da Vinci comes to our mind. During the Renaissance, Leonardo da Vinci sought to understand complex wholes by carefully analyzing their components. In studying the human body, he examined muscles and structures anatomically before integrating them into unified artistic representations. This intellectual movement between analysis and synthesis can also guide learning in complex contemporary issues. Climate change education may benefit from providing students with opportunities to analyze diverse elements and later reconstruct an integrated understanding. Slide 14. Building on the framework of analysis and synthesis, let us now consider a possible model of collective inquiry-based learning. How do students actually proceed in their learning? What kinds of processes do they follow in problem-solving activities? Although this is only a rough sketch, we may organize these approaches in the following way. In traditional lecture-based instruction, when a new unit begins, the teacher typically starts by presenting information, and students proceed with their learning along the direction that has been indicated. Sometimes specific activities are inserted during the lesson. When learning is organized primarily through group work, students may divide roles and collaboratively deepen their understanding of a single theme. This can be seen as a form of inquiry-based problem solving. In the past, there was an active discussion about student cognition from the perspectives of constructivism and social constructivism. Today, educators tend to focus not only on individual students' problem-solving processes but also on intentionally designing the collective process of learning as a community of learners engaged in mutual interaction. However, teachers who feel uncertain about how far students' interests might develop may provide a predefined list of topics. Students select one topic, investigate it in depth, and finally present their findings in a formal session with little genuine interaction. In such cases, meaningful collaborative learning is unlikely to emerge. Slide 15. When a learning community begins to engage with diverse concepts such as those involved in climate change education, a useful starting point is to draw out ideas that students have already heard about and to explore the relationships among them. Some of these ideas may be scientifically inaccurate, however, through discussion with one another, students may gradually become aware of ambiguities and misconceptions. After sharing an overall picture and recognizing how different elements are positioned within it, students can then deepen their understanding of a particular concept or topic individually or in small groups. Allowing students to choose their own themes at the outset is important for strengthening their sense of involvement and responsibility. Depending on the needs of their inquiry, activities may include conducting experiments, visiting science museums, consulting experts, or interviewing local residents. This stage represents the analysis phase, in which learning is deepened by breaking the whole into its constituent elements. It is also beneficial to schedule interim presentations along the way. Many high schools organize school-wide poster sessions, inviting younger students and parents to attend. In many cases, external experts are invited to provide advice. The ability to formulate meaningful questions, what we might call questioning competence, is another key factor in enhancing students' capacities. Some students may even wish to change their research themes during the process, while others may diverge from the original objectives. Nevertheless, a problem-solving process driven by intellectual curiosity that arises from within the students themselves becomes an irreplaceable learning experience. At the last stage, students can create a new concept map or revise the one they made at the beginning. In doing so, they will be able to recognize how their inquiry has deepened, how connections have expanded, and how their overall understanding has grown. Such experiences become meaningful when students graduate and face real-world problem-solving. The approach of analyzing the whole, deepening each part, and ultimately synthesizing them remains effective even today, centuries after the time of Leonardo da Vinci. If you agree, I would like to call this collective problem-solving inquiry model for understanding complex systems, the Gwangju model. Slide 16. Now I will move on to part 2, where I will introduce specific examples of student activities. Those are examples of what students come to grasp during the analysis phase. Slide 17. First, here is an example from the very early stage of understanding the issue. Some students may even question whether global warming really exists. In such cases, this is a practice through which students can become convinced that global warming is indeed occurring by using meteorological data from their own region. This is a method that young Shin and I presented in Japan about 10 years ago. This graph shows changes in the average temperature in Tokyo over the past 150 years. It may appear that the temperature has risen by about 2 degrees Celsius. However, it is possible to present data that are even more striking and more convincing for students. Slide 18. The orange line shows changes in the number of days when the daily maximum temperature exceeds 25 degrees, while the blue line shows changes in the number of days when the daily minimum temperature falls below 0 degrees. About 150 years ago, both hot days and very cold days occurred on roughly 60 to 100 days per year. In recent years, however, the number of days exceeding 25 degrees has risen to around 140. At the same time, it is clearly evident that days with below freezing morning temperatures have almost disappeared. Although this example uses data from Tokyo, similar graphs can be created for observation sites across the country. By analyzing data from their own local areas, students can confidently confirm, with empirical evidence, the testimony of older residents that hot days have become more frequent while cold days have become less common. Slide 19. Here is the second example. Among the themes that students may choose to investigate, some involve taking a long-term perspective and looking back historically. As a typical case, let us consider the relationship between sunspots and famines. Sunspots cannot be observed with the naked eye, so a telescope is required. They were discovered by Galileo Galilei, who built one of the first astronomical telescopes. Since the early 17th century, humanity has accumulated data on sunspots. Today, these data are compiled at the Royal Observatory of Belgium, and they are available online. This graph shows changes in the number of sunspots from 1700 to the present. As you know, the number of sunspots varies in an approximately 11-year cycle. In your country, in which years did famines occur? In the next slide, I will overlay the data from Japan. Slide 20. The year 1816 is known as the year without a summer. This followed the massive eruption of Mount Tambora in the previous year, which caused unusually cool summers on a global scale. It is said that snow even fell in June in the eastern United States. From the 18th to the 19th centuries, several such famines are known in Japan. What do you think? It may appear that famines tend to occur when the number of sunspots is low. However, they do not seem to happen regularly in the 11-year cycle. This kind of inquiry activity involves citing data from the Royal Observatory of Belgium and comparing them with the history of one's own country. Wouldn't this be exciting for students as well? Natural disasters often bring about social transformation. Unfortunately, I do not have time to introduce further examples today. Slide 21. Let us now look at the third example, which relates to contemporary energy supply. This example provides a different perspective on our present energy situation by focusing on nuclear power generation. The efficiency of nuclear power plants is often described as being about 33%. This figure is even mentioned in junior high school science textbooks in Japan. Now, let us consider a relatively large nuclear reactor that generates 1 gigawatt of electricity. In a reactor of this scale, a large volume of seawater is drawn in as secondary cooling water to remove waste heat. To minimize environmental impact, the discharged water is typically allowed to be only about 7 degrees warmer than the surrounding seawater. The amount of seawater used for this cooling process is said to be approximately 70 tons per second. 70 tons per second. Let us estimate the amount of heat released. The calculation is quite simple, at a level that high school students can handle in science class. If we assume the specific heat capacity of seawater to be 1.03 calories per g degree, and use the conversion, 1 calorie equals 4.2 joules, we find that roughly 2 gigawatts of thermal energy are released. This means that a power plant producing 1 gigawatt of electricity is simultaneously releasing about 2 gigawatts of heat into the environment. In total, the reactor generates about 3 gigawatts of thermal energy, roughly 1/3 is converted into electricity, while the remaining 2/3 are discharged as waste heat. In other words, when we warm ourselves with an electric heater, an additional amount of heat equivalent to 2 more heaters would be released into the seawater at the same time. This relationship is consistent with the commonly cited thermal efficiency of about 33% for nuclear power generation. What do you think? Even when we know that the thermal efficiency of nuclear power plants is about 33%, we may not fully realize that we are indirectly contributing to environmental warming through the release of much larger amounts of waste heat. Does this perspective help us reconsider nuclear power generation as an energy system? After gaining such insights, when students later learn about the thermal efficiency of different power generation methods, they tend to engage more seriously with the topic. They may also grow into adults who can critically evaluate simplified or biased claims, such as describing nuclear power as a clean energy source that does not emit carbon dioxide. Slide 22. Let us move on to the fourth example, which is closely connected to everyday life. This case involves my household system combining solar power generation, an electric vehicle, and a V2H system. I will skip the parts that many of you may already be familiar with. My car is a used one, and its battery capacity is about 60 kilowatt hours. Depending on the season, its average driving range is around 450 kilometers. V2H stands for Vehicle to Home, a system that allows the electricity stored in an electric vehicle's battery to be used in the home. With this system, it becomes possible to charge the vehicle using electricity generated during the daytime or purchased at a lower cost during the midnight, and then use that stored energy economically during peak household demand. Moreover, in the event of a power outage caused by a disaster, the electricity stored in the electric vehicle can temporarily be used to supply power within the home. Slide 23. Over the past 10 years, we have truly witnessed a historic transition marked by the spread of electric vehicles. The battery itself weighs about 300 kilograms. This is roughly equivalent to 5 adults weighing 60 kilograms each lying across the floor of the car. Of course, an engine is no longer needed, which reduces weight to some extent. However, electric vehicles often have relatively wide tires, partly because they must support the weight of the battery. If battery performance improves in the future, such wide tires may no longer be necessary. The relationships among factors such as battery capacity in electric vehicles, the availability of public charging stations, the spread of home charging systems, and the overall adoption of electric vehicles provide excellent thinking material for developing students' logical thinking. If public charging infrastructure expands, electric vehicles are likely to become more widespread. In this sense, it is a classic chicken and egg relationship. On the other hand, if technological innovation leads to the widespread use of advanced batteries, such as all-solid-state batteries, battery capacity will increase and driving ranges will become longer. In that case, a very large number of public charging stations may not be necessary, and the pace of charging infrastructure expansion could slow down. Even if more households install private charging equipment, public chargers will still be needed, since not everyone can install a charger at home. Therefore, charging stations must be developed as part of essential social infrastructure. Governments, energy companies, and automobile manufacturers are gradually promoting the adoption of electric vehicles while carefully maintaining this delicate balance and continuing to develop public charging networks. Simply by examining the relationships among these multiple factors, students can gain a deeper conceptual understanding of electric vehicles, and the significant educational value of such inquiry becomes clear. Slide 24. Now, let me summarize today's talk. In the first half, I proposed a problem-solving learning process that enables collaborative learning, which is essential when studying complex systems. This proposal drew inspiration from the idea of analysis and synthesis associated with Leonardo da Vinci, as well as from approaches such as the use of color solids. Just as Galileo Galilei named the satellites of Jupiter the Medicean stars, I would like to name this model the Gwangju inquiry and present it as a gift to Professor Park. Although similar practices already exist, I believe it is worthwhile to reconsider and articulate this framework once again. In the second half, I introduced 4 examples of student learning that correspond to the analysis phase, in which individual topics are explored in depth. These included an example focused on recognizing and understanding the problem itself, an example examining issues from a historical perspective, an example offering an alternative way of viewing contemporary nuclear power generation, leading students to recognize the direct human effect on global warming, and finally, an example concerning energy choices closely connected to students' own daily lives. Slide 25. As students engage in these learning experiences, the concept maps they created at the beginning are also revised. New labels may be added, new links established, and their conceptual understanding is gradually reconstructed. This reconstruction itself represents an important outcome of learning. Such a perspective can be traced back to the pragmatism of John Dewey and is also connected to more recent research in constructivism. Slide 26. I hope that at least 1 or 2 ideas from my talk today will serve as useful hints or inspiration for your future research. Thank you very much for your kind attention.